As we move on to talking about specific forces a little bit more in depth, we first need to start off by clarifying some ideas. So the first one is mass versus weight. Often we seem to interchange those two terms when in fact they are entirely different. So mass is how much stuff there is, how much matter there is in an object. So you can think of it like this. Think of the periodic table. I am made up of a certain number of atoms of carbon, oxygen, hydrogen, etc. And all of those atoms have a certain atomic mass, right? And so we should be able to just take those atomic masses, multiply by the number of those atoms that are in my body, and find my mass. But if I were to fly to the moon, I would weigh less, right? I can jump much higher, jump much farther. I feel less heavy. There aren't fewer atoms of me, though, right? If we would still do the same thing and calculate my atomic mass by all of the atoms in my body, I would still have the exact same mass, but the way that that mass interacts with the gravity of the planet that I'm on, or the body that I'm on, changes. So mass is how much matter there is in an object, and weight is how that mass interacts with gravity. Okay, so mass is the amount of matter, and that's measured in kilograms. Weight is the force of gravity acting on an object, and that is measured in newtons, because force is measured in newtons. So when you're asked how much do you weigh, that's really not a good way of asking what that person wants to know, because your answer should technically be in newtons, right? So you would need to know how hard the earth is pulling on you, right? You'd have to answer in newtons. What they're really wondering is what's your mass. So weight can be calculated using F net equals ma, because it's a force. But the a that we are talking about is specifically the acceleration due to gravity. Okay, that would be ag or just g. Okay, so that's the acceleration that we're talking about. And so then your weight, or the force of gravity, is mass times the acceleration of gravity. And the acceleration of gravity is always 9.8 meters per second squared when you're near the surface of the Earth. Okay, that's going to change if you move to a different planet, or if you go into orbit around the Earth, then it's going to be a little bit less than 9.8. But most of the time what we are going to be doing is regular everyday experiences near the surface of the Earth. So, for example, a small rocket has a thrust of 650 newtons up after launching. If the mass of the rocket is 50 kilograms, what is its acceleration? Now, we're assuming that this rocket is still near the surface of the Earth. It's not in orbit yet or anything like that. So the acceleration of gravity that we're going to be using is still 9.8. So we are looking for the rocket's total acceleration. We're not being asked what's the acceleration of gravity. We know that. We're asked for what's the total acceleration of the rocket. So that's A equals something. We are told its thrust force, so we're going to call that Ft. That's 650 newtons up. We are told the mass of the rocket, 50 kilograms. And that is all we're told. We also do know the acceleration of gravity, which is 9.8 meters per second squared. That's down though, right? So what we're going to do here is actually get rid of this up and instead call this positive and this negative. So everything that's happening in the up direction is going to be positive. Everything that's happening in the down direction is going to be negative. So I'm going to put that key in right here. that up is going to be our positive direction and down is going to be our negative direction. Okay, and so our acceleration of gravity is negative 9.8 and our force of thrust is going to be upward, positive 650. So what we're looking for is total acceleration, and we're going to get that from F net equals ma, because what this equation means is total force, or the sum of all the forces, is equal to the mass times the total acceleration. And so this A is what we're trying to solve for. Now, often what you're going to do when solving dynamics questions is you're going to look at what are all the forces acting on this object, and we're going to take F net and split it into all of those forces, because those forces, 650 newtons, and the force of gravity, we're going to need to put those together. So, splitting F net into the force of thrust and the force of gravity. Now I'm going to make the force of gravity negative. So I've taken care of this negative in the 9.8 already. I won't need to put the negative in the 9.8 when I put it in the force of gravity formula. Okay, we shouldn't use it twice. Thrust minus gravity equals mass times acceleration. So I'm trying to solve for this A over here. So I'm going to divide by m. Now it's important that I divide this entire side by m. Okay, I can't just pick one of them and divide it by m. So I'm going to end up with thrust minus gravity, the force of thrust minus the force of gravity, divided by the mass of the rocket is equal to the total acceleration of the rocket. Okay, so now if this was a simple, straightforward question, perhaps I could just take all the numbers from the question, plug them into these three spots, and solve for acceleration. But unfortunately, I am not given the force of gravity on this rocket. I'm going to have to figure that out. So sometimes what you're going to find is that when you do this, the forces in this formula, the forces in your F net formula, have their own individual equations. So we just learned that the force of gravity is mass times 9.8. Right? So now we can write the force of thrust. The force of thrust, we already know that number. It's 650 newtons, so we don't need to expand it into its own individual equation. But this Fg is mass times 9.8. Okay? And so whenever you see the force of gravity here, you're probably not going to be given the force of gravity in the equation, but rather you'll have to expand it into its formula. And we can't forget this divided by m here, because that was in the previous step. So now if we look at all these pieces, we know that the force of thrust is 650 newtons. We know the mass of the rocket is 50 kilograms. We know g is 9.8. We know the m on the bottom is also 50 kilograms. And so we've filled in all the pieces that we need to solve for that acceleration. So now we can throw in our numbers and just do some algebra to finish that solving. So the force of thrust is 650 newtons minus the mass, which is 50 kilograms, times 9.8 meters per second squared. And I'm going to take all of that and divide it by the mass again. And that is going to give me my total acceleration of this rocket. Some things to point out. Notice, as I said before, I did not put the negative by the 9.8 here. I did put a negative over here to show that this is down, but I took that negative and I just put it out front of the entire term here. And it doesn't matter whether you put the negative here or whether you put it out front of the term or whether you put it inside the term with the acceleration. It has the same effect. And so I just assigned a direction to the whole force of gravity rather than assigning it to the acceleration. Okay. Now, the second thing, some people find that they want to take the mass from the bottom over here and they want to cancel out this mass from the top. Now, you cannot do that because this bottom mass applies to both the 650 newtons and the 50 times 9.8. So you can't just cancel it out from one of those terms and then say you're finished with it, because you still need to divide the 650. So we're just going to do this whole thing, 650 minus 50 times 9.8, and then we're going to take that answer and divide it by 50. And we end up with an acceleration of 3.2 meters per second squared, positive 3.2 meters per second squared. And what that means is up, right? So whenever you get a positive answer, it should match with what the positive direction was in your key from the very, very beginning, however you decided your directions. And so our final answer is the acceleration of the rocket is 3.2 meters per second squared up. Now notice that I didn't just shove an up on this answer over here, because I don't want to mix signs like this with directions, because often when you have a negative sign in your answer and you shove a direction on the end of it, you've actually done something that you didn't intend to do. So if my answer was negative 3.2 meters per second and I went, oh, that means down, then I'd put negative 3.2 meters per second squared down. What I've actually said is negative down, which is up. I didn't intend to say up. And so I always ask that you translate your positive or negative sign into the direction. So notice that I did not put a positive or negative sign in front of the 3.2. I translated that into the direction. For the second one, we have a 50 kilogram person in an elevator, and they're on a spring scale attached to the ceiling, or they're hanging from a spring scale that's attached to the ceiling. What is the reading on the scale when the elevator is rising with an acceleration of 2.5 meters per second squared? Now this is not a common run-of-the-mill situation you're ever going to find yourself in, but it's an interesting thought experiment anyway. And so we're going to draw a little picture of what's going on here. So here's our spring scale. Let's say it's somehow attached to the ceiling. Here's a hook attached to the ceiling. And then there is the spring scale part. You know what a spring scale looks like, hopefully. And then there is the person who is hanging from the spring scale, but they're hanging by their arms, so you know everything's fine. Okay, now the spring scale reading is telling you how hard the spring is pulling on the person to keep them holding still there. Okay, so what we've got here is a force of gravity pulling downward, and we've got a what I'm going to call spring force, but really you could call it a force of tension or something like that. We're going to call it Fs, just the force from the spring scale. Okay, so we have the force of gravity pulling down, we have the force from the spring scale pulling up, and this person is within the elevator. They're not falling in the elevator or rising in the elevator, but the entire elevator is rising. Okay, so this whole contraption, the person, the spring scale, the elevator itself, is all rising at 2.5 meters per second squared. Okay, so here's our situation. We are looking for the force due to the spring scale. What's the reading on the scale? So we're looking for Fs. Notice how I always just pick out, first of all from the question, what is my end answer supposed to be getting at? So the spring scale force is the thing that I'm looking for. Then, from beginning to end, I've got the mass of the person, which is 50 kilograms. I've got the acceleration of the whole thing. That's total acceleration is 2.5 meters per second squared. And that acceleration is upward, so I'm going to call that the positive direction. Okay? Other things that we always know that are involved here is g, the acceleration of gravity, and that's going to be negative 9.8 meters per second squared. And so now we're trying to figure out this Fs part. we are given total acceleration. We're looking for the spring force, so we know that this has got to have something to do with F net equals ma. So we're going to start with that. F net equals ma. And just like most of the time when we're working with F net equals ma, we're not told exactly what F net is, but we're told what the different pieces are. So we're going to split F net into the forces acting on this person, and those would be the spring force and the force of gravity. The spring force is going to be upward. The force of gravity is going to be downward, so I'm making that negative. I did, again, put a negative on the 9.8, but I'm taking that negative and putting it out front in the force of gravity, so I don't also need to put it in the 9.8 now. Equals ma. Okay, now, I do not know the force of gravity, but I can calculate it using mass times 9.8. I know this mass, which is 50 kilograms, and I know the total acceleration. And so the missing piece is going to be this spring force. So I'm going to add the force of gravity to the other side so that I can isolate the spring force. So this is ma plus Fg. Okay, but I don't know what the force of gravity is, so just like in the previous one, I'm going to expand that into its equation. Okay, so now I have ma plus mg, let me fix this, this should be an a, not a g, equals the spring force. Now, I know all of these numbers, so I can just put them all into my formula here. The spring force is equal to 50 kilograms times total acceleration, which is 2.5 meters per second squared, plus 50 kilograms times 9.8 meters per second squared. Okay, again, because this is going to pop up all the time, I didn't put the negative in the 9.8 over here, right over there. I didn't put in the negative there because I already put it in way over here. And then all of the algebra steps that I took after that all took that negative into account. Okay, so even though I am 3 steps down from where I initially put in that negative from the 9.8, I shouldn't forget that I've already dealt with it. Okay, so I don't need to put it in there as well. So now my spring force is equal to 50 times 2.5 plus 50 times 9.8, which is equal to 615 newtons up. Right? It was positive, and so my positive, I should have done this at the very beginning, but I chose up as my positive direction and down as my negative direction. And so I got a positive answer for my spring force, which means that corresponds to up. Now, this is not the correct number of sig figs. Okay, I'm not always very picky about sig figs, but it's a good habit to be in to make sure that you have the right number of sig figs. So this has 3, this has 2. We're not going to take into account the 9.8 from gravity because that is not a measured value from our question. And technically we could research how many decimal places we know at our particular location. And so we're not going to take that into account for sig figs. We're only going to take into account the 2 values from the actual question. And so this has 3 sig figs. This has 2 sig figs. And so our answer should be rounded to 2 sig figs. And so that gives us a spring force of 620 newtons up. And that would be including significant figures. Okay, you don't have to put significant figures in brackets all the time, but for the sake of the notes here, I think that I wanted to put that in for clarity.